right? This is 0 and this is 2 pi. If I take the integral of sine between 0 and 2 pi, that is going to give me 0.
Correct. Absolutely.
Even though the area is not 0. It's because we are measuring the net result of the areas.
I see. So just because you have positive area here, you're not counting the area of this particular section because it is canceled out by the equivalent negative area.
Yeah, exactly.
I see. So if this area was A from here to here, and this area was A from here to here, then plus A and minus A, you're saying that would cancel?
Exactly. That's how we do it.
Okay, so we're not just finding the area under the curve, we're finding the net area.
Yeah.
Okay, sounds good. So so we're going to continue from this point here, right? Where we're going to find the area of the triangle and add that to a negative area, which is pi r squared over 2. And I guess let me just erase some things maybe for space, or let me
yeah, sure.
maybe
Let me
just
erase that graph.
Section it off here. Okay, sounds good. So we do 1/2 times the base. Now I would assume, Victor, that the base is essentially going to be this particular section here, which is -4.
Yeah, but here we don't need to make things with sign.
Could you explain?
Because here we are just thinking geometrically. Like the base, this has a length of 4. That's all we need to know. So we are going to use 4 for that.
So you don't want me to use the sign negative?
No. In the case of the length, of finding the length of the base, no, we don't use -4. We just use 4. The sign just comes with the area.
And is there any reason as to why we don't consider the sign of the number of the base?
Well, there's no reason why we should really, because here we are just looking at a triangle, right? So this triangle, I mean, it's the same triangle wherever I put it. So here, as long as it has the same dimensions, it's the same triangle. We are trying to figure out the area. So it goes from 0 to -4. So the length is going to be 4.
Well,
here I'm not worried about the sign part.
Well, it seems like over here you are worried about the sign part, but over here you're not worried about the sign part.
Yeah, but that's not because of the particular length of the radius or something. It's because the picture, the figure itself, is below the x-axis. That's all I'm worried about.
Okay.
So like here, if I calculate the diameter, that's going to be 4.
Right.
But that doesn't have anything to do with it. It's positive, but we are still getting a negative area.
Okay. Well, let me ask you this, Victor. What if we had something like 1, 2, 3, 4, maybe something like this, right? Or actually, yeah. So would we say that the diameter is -4?
No, the diameter is 4. If you look at it and you take a ruler and put it there, it's going to give you 4.
So we don't use the x-axis in terms of sign here.
No, we just look at where the picture is. Is it above the x-axis or below?
Okay.
We get our sign from there, okay?
Yeah.
So when looking at the length, we always use positives. we are going to apply the signed area looking at the picture itself. Is it above or below? And then we apply the sign.
I see. Okay. So what? If I had something like this, 1, 2, 3, 4, maybe something like this, it would be negative 1/2 times base times height.
Yeah.
And then I would have something like this maybe. So this would be plus pi r squared over 2.
Exactly.
Or maybe pi r squared
Yeah,
over 2 minus 1/2 times base times height. Would this be the case for this one?
Not this one, because here you. Oh, sorry. Oh, yeah. Oh, no. It's this one. Sorry. Got confused. Yeah, those are both correct.
Okay, so.
Yeah, that's how you do it.
What if, one more question, sorry. What if I had.
That's okay.
What if I had something like this? One second. Something like this, maybe. Would this be negative 1/2 times base times height minus pi r squared over 2?
Yeah, exactly. Then everything is negative since everything is below the x-axis.
And b would equal, in this case, if I were to have 1, 2, 3, b would equal 3 and not negative 3.
Yeah. The length is always positive.
The length
There's no way the length is negative.
Okay. Because what does it mean to have a negative length, right?
Yeah.
But what about the height? For instance, if we go back to our original question here, the height would just be, in this case, I'd assume it would be 3 here, right?
Yeah. I mean, the height is whatever measures this side is.
Which side? Oh.
So if this side is here,
yeah.
That one.
So if this was 3 here, it's not negative 3. It's 3 for the height.
Yeah. I mean, the point itself and the y-axis is negative 3, but we consider it with a length of 3.
Okay. So in the original question, we would have a height of about 3, right?
Yeah, I think that's it.
Or actually, in the graph that I'm looking at is actually 0, 1, 2. So this is actually 2. 0, 1, 2.
Yeah, 2 height.
Okay, so let me try to erase some things. Can you clear the board by chance, so we can have some space to write some things?
Everything, or just
no, just some section. Maybe just the right hand side.
Yeah, sure.
Yeah, that's fine. So I guess we have a plus here. So 1/2 plus, or multiplied by 4, not negative 4, times the height, which is 2, and adding that to negative pi times the radius, which we said was 2, squared over 2.
Yeah, perfect.
So this would just be 4 plus negative 2 pi, or 4 minus 2 pi.
Yeah, that looks about right.
Okay, awesome. Cool.
4 minus 2 pi.
I do have, so this would be the final then.
Yeah.
Okay.
That should be.
Yes, that's okay. Awesome. I actually do have another question, if you don't mind.
Sure, we can do that.
On whiteboard 2.
Yeah, I'm on it.
Okay, so so the question here is to find the antiderivative. And let me ask you this: when we use this notation, what do you say you are finding? Do you say that you're finding the antiderivative, or how do you express? Like, for instance, if I say d over dx of, let's say, f of x, I verbally say that I'm finding the derivative. But when you use this notation, what do you say you are finding?
You are finding the net area under the curve between 1 and 0.
Right, but just in a casual sense, do you say that you're finding the antiderivative?
No. The antiderivative is just in the case where there's nothing on the top and bottom. So,
right.
This is the antiderivative or the primitive. And you can also call it the indefinite integral because it's not defined on the bounds here. But this is the area under the curve or the definite integral.
Right. And what exactly do you mean by primitive?
Primitive is just it's the same as the antiderivative. It's just another word for it.
I see. So finding the primitive is the same thing as finding the antiderivative?
Yeah.
Okay. Awesome. Cool. So let me go ahead and just write the question down, and we'll work from there, I guess. So the question is to find, I suppose, the primitive on this particular interval of the function x squared with respect to x plus
in this case, you don't say the primitive.
Oh.
You say the area or the definite integral.
But, okay. Okay, I only say the primitive when I'm referring to the integral between 1 and 0. Okay, so I only use the terminology primitive when referring to indefinite integration.
Yeah, exactly.
Okay. Okay. So this is essentially the question here.
Okay. So what do you think we can do here?
Well, unfortunately, I only know one part of this question for sure, which is that this particular section here goes to 0 because if we had a curve, I guess the curve of x to the third in the first quadrant, which looks something like this, then we can't find the area of a particular point. So this would go to 0. But this is essentially what I'm confused about, this part here.
Yeah, so that's kind of new, right? So the problem here is that these are switched.
Switched.
The bigger one is on the bottom, and the bigger one is on the bottom, and the lesser one is on top. That's not really supposed to happen.
So in normal cases, the bigger one will always be on the top?
Yeah. On the way we kind of define integrals, the bigger one is always on top here. Okay, so b is always bigger than a.
Correct.
But we have a way to deal with this. Okay, so when we switch the limits of integration, we are going basically to switch the signs. So the thing is, the number itself is the same, but the signs are switched.
Is there any particular reasoning behind why this is the case?
I mean, it's kind of a natural way to think about it.
Sure.
It's because we don't really see in real life applications things like this. Okay, it's just a way for us to deal with the limits being backwards. Basically.
Right. I see. So maybe because like
so it's like just convention.
Huh?
Oh, sorry. It's just like notational stuff.
So I guess
there's no real reason for it.
So like maybe this is like a guess. If I had, let's say, B and A here, I'm finding the area of the curve going backwards, maybe. So that's why it's negative.
Yeah, that's the idea.
Maybe that's why. Yeah, it's just
we
a
kind of
guess.
go backwards.
Right. You were saying?
Yeah, but that's the idea, I think. But I'm not really sure of the real reasoning.
Sure.
Maybe there's some kind of property that we want to preserve this way by doing this. But I can't remember in the top of my head. But it's basically how it works. If you switch the limits, then you switch the sign.
Actually, I think. One second, Victor. So I think this is maybe the case. For instance, if I had something that looks like a regular integral, let's say here, this would be the normal case, correct?
Yeah.
Which would equal
where B is bigger than A.
Right, where B is greater than A. So where B would be greater than A. So we would take f of B and minus it from, or minus f of A from it, right?
Yeah, there's the reason.
But
it's to preserve the fundamental theory of calculus.
Correct. But I think when they're reversed, like when we reverse it, we're actually talking about f of A minus f of B, right? Which would be negative.
Yeah.
So they factor out a negative sign.
Yeah.
I think so.
And that is the reason.
Yeah, it's in my book here, actually, on the chapter. In a particular chapter, I think they factor out the negative and then they switch. So once they factor out the negative, they switch the, they then make it as it would be regularly. Or, sorry, I think they factor it out and they switch it around.
Oh, that's right.
Yeah, and that's, I think, why. That's what it says according to my book, I think.
Yeah, that's correct. Yeah, I just couldn't think about it at the time, but
yeah.
But yeah, that's why when we switch, we get a negative because of the fundamental theorem of calculus.
Absolutely, absolutely. So I think we can erase all of this stuff here and then return to the question.
Yeah,
maybe.
sure. Let me erase that.
Actually, how do you erase so quickly at once?
I use the marquee tool, the one that creates a square where you can select things.
I see. I see.
And then I just press the line.
Okay, awesome. I also found this.
Yeah, so anyway, let's.
Huh?
What?
I was saying I found this over here on the side in the tools.
Oh, that's nice.
Yeah. So how would you, so you would switch them around is what you're saying?
Yeah.
So you would get negative.
And then to account for that? Yeah, exactly.
Okay. And then do we solve as we regularly would?
Yeah, we can do that. We can do a little trick to make things easier, but it's not a big deal.
Okay.
See if you can find it, maybe.
So,
but don't worry about it too much.
We would take the integral of this and this.
Yeah.
Okay. So that would be x cubed over 3 negative.
Exactly.
And then this would essentially be f of x. So if we were to evaluate, we would essentially have f of, let's see, 1 so this would be what we would have here. And for this one, we could have the same thing.
Yeah.
So it would be minus 1 over 3 plus 9.
Yeah, perfect. I think that's right.
Okay. And you were mentioning a trick, maybe? I think that's what you said.
Yeah. It weren't going to do much of a difference, but if you think about it geometrically, what is the first integral doing? We are taking away this area between 0 and 1, right?
Yes.
So I'm going to put that in red. And the second integral is calculating the area between 0 and 3. So let's say this. So we are taking this whole area. So at the end, we just need to calculate the area between 1 and 3.
Right. So
yeah.
we're
that
just
wasn't going to make much of it.
So we're just finding
Yeah.
I see. Okay, interesting. So that's the geometrical relevance there.
Yeah, exactly.
Okay, sounds good. I think that's all the questions that I have today.
Okay, great.
Awesome.
Yeah, always good working with you.
Yeah. Thank you for being here, Victor. Hopefully we can work together again sometime.
Sure, I hope for it too.
All right.
Have a nice day.
You too.
That's all.
Bye.